Hi everyone. So today's topic is scatterplots and correlation. So these are the key points from the previous lecture. We learned how to compare two different distributions and outliers and moving averages, smoothing, and re-expressing data. And also we learned a normal model, and in the class we learned how to draw normal probability plots. Today we will learn scatter plots, and already from the normal probability plots you actually already learned how to draw scatter plots, because the normal probability plots are actually scatter plots. Okay, so we are using dots for scatter plots. We are using dots to show the relationship between two variables. This is an example data from the textbook, and x-axis here is year, and y-axis here is a prediction error of the hurricanes. So it's nautical miles of the predicted position of Atlantic hurricanes. The predictions were made by the National Hurricane Center of NOAA. NOAA is the National Research Lab of the weather and stuff. So against the years, over time, the prediction error decreased, right? That means the prediction model gets better and better over time. So this scatter plot, this type of visualization, is the most common display for data, one of the basic building block of the data visualization. And this is a famous quote by Yogi Berra, because this really applies to the scatter plots, because scatter plot aim to show everything, raw data. In this previous example, this is showing the relationship between only two variables, but we can also show the relationships among multiple attributes, multiple variables. Here is showing cars, I think, and each from different countries, and horsepower, weight, and acceleration, and displacement. And for example, this shows the relationship between horsepower and weight, and this plot shows the relationship between weight and acceleration. This plot shows the horsepower and acceleration, and so on. This is from this website. This website has a really nice visualization, and I actually want to show you the site, and this is the site. Yeah, let's see if I can show you. Like, this is an interactive plot. You can actually visit the website, so you can choose the area and data and show the relationship among these variables across multiple plots. And also, this is from this website. So this is the whole website that has a lot of interesting visualization styles. Yeah, like that. It's interesting, right? So you can change the years and obesity rate. So you can explore the website. So when examining the scatter plot, be sure to study the direction. What's my sign? Positive, negative, or neither? And also you need to look at the form. Is that straight, curved, or something exotic, or no pattern at all? And strength. How much is scatter? How much is spread? And outliers. Are there outliers or subgroups? You need to examine all these things by looking at the data. Let's go over each one. So the first one is direction. So there are positive and negative direction. For the positive association, as x increases, y also increases. So it shows this direction, okay? And for negative association, as x increases, y decreases. Then the shape is like that. So this direction. And we need to look at the form. What does the data look like? Is the data clustered together, or does the data have a linear shape or a curved shape? So this is clustered and linear and curved. Only with the scatter plot you can examine these shapes. And strength, the association strength. How closely do the points follow a clear form? So for example, this is clearly shows the linear relationship, but this a little more spread. Less clear than this, but it's still showing the linear relationship. Last one is outlier. Outliers can be determined from the graph by looking for points that are not within the overall pattern of the data. So here, this is a nice linear relationship, but there is one dot here. This we can see by eyes, we can see this is an outlier. So could be many different questions, and the first thing we need to do is to define the variables. What is x? What is y? And what is the dots? Okay, so let's examine each question. So the first question is, do baseball teams that score more runs sell more tickets to their games? So here, each data point is team, and x the score, y as tickets they sell. Okay, then we can show the score and tickets, these relationship. Each dot should be team. Do older houses sell for less than newer ones for comparable size and quality? In here, in this question, each data point should be houses with similar size and quality. And x should be age, and y should be the price of the house. X is age, y should be the price, and you can locate the many houses with a similar size and quality. Okay, I think it should be negative relationship, older houses, price less, I guess. And the next question is, do students who score higher on their SAT tests have higher grade point averages in college? In here, each data point should be students, and x is set score, y as GPA in college. The last question is, can we estimate a person's body fat more simply by just measuring waist or wrist size? And each data point should be person, and x is person body fat, and y is waist or wrist size. And here we have names for x and y. For x, we call it explanatory variable or predictor variable or independent variable. And y, we call it the variable of interest, and response variable, and dependent variable. Because we define y based on x, x is independent variable, but y is dependent on the x variable, so it's dependent variable. In here, in this example from earlier slide, x is year and y is prediction error. So we want to know the pattern of prediction error. It's decreasing over time. Okay. And usually the most common relationship we are interested in is linear relationship. So if the form of the plot looks like a line, this indicates there may be a linear relationship between two variables. The relationship is strong if all the data points approximately make up a straight line. It is weak if the points are widely scattered. Based on this, the correlation is defined. Correlation is a really common measure for the strength of a linear relationship. So correlation provides the information about the strength and the direction of a linear relationship between two quantitative variables. Correlations are usually denoted by R. So R equals something. Okay, I want to tell you more about the correlation. There are two scatter plots here, and what is the difference? Okay. Can you find? Yes, the scales are different. So left side plot, we are using pounds and inches for weights and heights, and in the right side, this plot using kilogram and centimeter as its scale. But the shapes are same because they only just doing the rescale. The units should have no effects on our measure of strength of a linear relationship because they should have the same measure for the strength. Therefore, we can use z-scores. As we learned in the previous lecture, z-score doesn't have a unit. So here, this is the z-score, height and weight. So this is a good plot. So we actually can make measure using the dot product zx times zy and sum it up, and then it'll tell us the strength of a linear relationship, because if that has a linear relationship, there should be more dots in this and this than this and that. So if the dots have the same sign and negative sign, it should have the larger value. So this can be perfectly telling us the strength of a linear relationship. So we can define the correlation coefficient using this, because the sum of the zx times zy is actually, if they are same, zx times zx, sum of this is n-1 because of definition, because it's divided by standard deviation. This value from -1 to 1. So correlation value ranges from -1 to 1. There is another different expressions, but mathematically they are same. This is exactly same with this. Yeah, as you can see here. There are assumptions and conditions for correlation. The first one is quantitative variables condition. So the values should be quantitative variables, and straight enough condition. So when we look at the value dots, it should be straight enough. Then we can use the correlation, and there should be no outliers, because outliers can distort the correlation dramatically. And there are properties of correlation. We can say the direction of an association, whether it's positive or negative, using the sign of correlation. R is always between -1 and 1. It's designed to have this range. When R equals 1, all of the points lie on a straight line, perfectly straight line with a positive slope, like this. And R is negative. That indicates a negative association, like negative association, this direction. When R equal -1, all points lie on a straight line with negative slope, like that. If R is close to 0, this indicates a very weak linear relationship, like this, just spread dots. The correlation of X with Y is same as the correlation Y with X. And the correlation values has no units. And only linear correlation measures only the strengths of a linear relationship. If the two variables has this quadratic relationship, the correlation cannot detect this shape. And correlation values are sensitive to outliers. Okay, so far I've talked about parametric correlation measures, but there are other types of correlation measures like non-parametric ones. And one is Kendall's tau. They can be used for Likert type scale data, that is ordinal variables. So Likert type scale is like this. You see this very often in many types of surveys. The interval between 0 and 1 could be different from the interval between 1 and 2. Just it's showing, giving us the order. 1 is larger than 0 and 2 is larger than 1. So that's why we call it ordinal variable. In this type of variable, there's the distribution of the data should be quite different from the continuous values. And because it tells us only the order, what's larger than the other value, we compare all pairs of the data, and if that has this direction, it's concordant pairs, and then this negative direction, we call it discordant pairs. And by comparing all the possible combinations, pairs of these data, we can count the number of concordant pairs, and also we can count the number of the discordant pairs. Subtract the number of discordant pairs from the number of concordant pairs, and then divide this by this number, all the possible pairs. It is ranged from -1 and 1, because if all the pairs are discordant, it should be -1, and if all the pairs are concordant, and then it should be 1. And there's another one, it's called the Spearman rule. It's really simple one. If the original data is a continuous variables, after you sort the data, you replace those original data with ranks, like 1, 2, 3, 4, 5, and so on, and then calculate the correlation. Usually, if the distribution is similar to the normal distribution, Spearman correlation and Pearson's correlation, they are similar, so there is no much difference. But if there is an outlier like this, the Spearman correlation is different from Pearson correlation. And the important consideration for correlation is the correlation doesn't mean causation. So we as a human, we tend to see causes and effects in everything. And this is an interesting data. So here x-axis is the number of storks, this bird, and y-axis here is human population. And as you can see, there's a clear positive relationship between number of storks and human population. Because of this, people thought storks bring more babies. You might know this movie. There is a movie, the birds bring baby. But in fact, if there is more people in the city, there should be more houses. That means there are more nesting sites, and then that means more storks. So different from what people thought, the truth was the opposite direction. We call these as lurking variables, these intermediate variables. That's a hidden variable that simultaneously influences the other two variables. Therefore, the scatter plots and correlation never prove causation. There are a lot of cases the lurking variables play a role, important role in the relationship between two variables. I want to show you the correlation table. It shows the relationship between two variables, like this number is the relationship between sales and assets, and this is market value and assets. And because this is also sales and assets, the relationship between sales and assets, the number should be same, right? So therefore, we just omit this and then only show the bottom triangle or top triangle. So symmetric matrix like this, and this is showing the correlation using this upper triangle. The diagonal of this matrix should be 1 because it tells us about the relationship of this variable with itself. For correlation, we had these assumptions, but what if the relationship is not straight enough? If the scatter plot shows a bent shape that consistently increases or decreases, we can straighten the relationship by re-expressing or transforming one or both variables, like log transform or square root. Okay, we will learn more about re-expressing and transforming in later lectures. Okay, so these are the key points. The scatter plot that has direction, form, and strength and outliers. We can look at this by eyes, and we talked about x and y variables, explanatory independent, we call x variable with these names, and response dependent variables for y. And we talked about correlation, that provides an information about strength and direction, and correlation has the assumptions like quantitative variable condition, straight enough, and low outlier condition. And there are non-parametric correlations. And correlation is not same with causation, and we talked about correlation table and matrix. Okay, so that's it for today's lecture, and there will be some questions, and in the class we will talk about correlation further. See you in the class.